Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, you're good to go. You're still following me, right? Okay, today we'll continue our discussion on still internal memory. Okay, main memory. I always say main memory, but it's actually internal memory. Okay. So we have discussed RAM on our last lesson, and today we move to ROM. Okay. So actually there are many types of ROM. Okay. So as the name suggests, that a ROM read only actually not read only, read only memory. It contains a permanent pattern of data that cannot be changed because it can only be read. But a ROM is non-volatile, means that actually we need no power to maintain the bit values the memory. And while it's possible to read ROM, or to read a ROM, I mean, it's not possible to write new data into it. Okay. So actually, ROM are mostly used in microprogramming, but also sometimes you use in library subroutines, or frequently wanted functions, a system programs, or even function tables. A ROM is created like any other integrated circuit chips, and yeah, with the data actually write into the chip as part of the verification process. And actually, there are two problems here. The data in system includes a relatively large physical cost, where one or thousands of copies of particular ROM are fabricated, and there is no room for error. If one bit is wrong, then the whole batch of ROM must be thrown out. Okay, so when only a small number of ROMs with a particular memory content is needed, the less expensive alternative is to use PROM, programmable ROM. It's also like the ROM. The PROM is also non-volatile and may be written into only once. But for the PROM, the writing process is performed electrically and may be performed by a supplier or a customer at a time later than the original chip verification. That we use special equipment to do this. PROMs thus provide flexibility and convenience, and it remains attractive for high volume production runs. And there is another variation on ROM, okay, okay, which is the read mostly memory, which is actually used for application with the read operation are far more frequently than the write operation, but which non-volatile storage is required. Actually, there are three forms of read mostly memory, which are EEPROM, double EEPROM, and flash memory. The first one is optically erasable programmable read-only memory, EEPROM, which is read and written electrically as with PROM, but before a read operation, the older storage cells must be erased to its initial state by exposure of the package to ultraviolet radiation. And the erasure is performed by shining an intense ultraviolet light through a window that is designed to the memory chip. Okay, and this erasure process can be done repeatedly. Okay, thus EEPROM can be altered multiple times, and like the ROM and PROM, it holds its data virtually indefinitely. Okay, so EEPROM is more expensive than PROM, but has the advantage of the multiple update capacity. And a more attractive form of read mostly memory is that of electrically erasable programmable read-only memory, which is double EEPROM. This is read mostly memory that can be written to at any time without erasing the prior contents, and only the byte of bytes address are updated. And the write operation takes considerably longer than the read operation, on the order of several hundreds microseconds per byte. And the double EEPROM can combine the advantage of non-volatility with the flexibility of being updatable in place and using ordinary bus control at the same data line. Okay, and double EEPROM is more expensive than EEPROM. It's um, clear, it's very clear, but it is also less dense, which support fewer bits per chip. Another form of semiconductor memory is flash memory, okay, because the speed of it which can be reprogrammed. Okay, so it's intermediate between EEPROM and double EEPROM in both cost and function making. Same as double EEPROM, that the flash memory using electrical erasing technology. The entire flash memory memory can be erased in 1 or a few seconds, which is much faster than the EEPROM. But it is possible to erase the block of memory rather than an entire chip. Okay, that is flash. However, this doesn't provide byte level erasure. Okay, so flash memory uses only one transistor per bit and so achieve the high density of the EEPROM. Next, we'll discuss about chip logic. So actually, each chip contains an array of memory cells. Okay. So for semiconductor memories, one of the key design issues is the number of bits of data that may be read or written at a time. And at one extreme is that an organization with a physical arrangement of cells in the array is the same as the logical arrangement of words in memory. Okay, this is the arrays organized into W words of B bits each. Okay. Yeah. So you see here, first physical arrangement are possible. In any case, that the elements of an array are connected by both horizontal and the vertical lines, and each horizontal lines connect to the select terminal of its cells in its row, and each vertical line connect the data in or sense terminal of each cells in its column. Okay, and you see address lines supply the address of a word to be selected, and a total of log base 2 W lines are needed. Here's the configuration of the example of 16 megabit DRAM, which is for M times 4. Okay, so the figure above indicates that the inclusion of refresh circuitry. So actually all DRAMs require a refresh operation. And a simple technique to do this is to disable the DRAM chip while all the data cells are refreshed, and the refresh counter steps through all of the row values. And for each row, then the output lines from the refresh counter are supplied to the row recorder, and the rest line is activated. And this can cause the row to be refreshed. Next is chip packaging. Okay, so maybe I'll not explain it too long. Yeah, you can see there's typical memory package and pin signals. I will go to memory organization. Okay. Okay, it's also kind of not very important. Interleave memory. Okay, so here, main memory is composed of collection of DRAM memory chips, and number of chips can be grouped together to form what I call a memory bank. And it's possible to organize the memory banks in a way known as interleave memory. So each bank is independently able to surface a memory read or write request, so that a system with K banks can surface K requests simultaneously, increasing memory or write rates by a factor of K. Okay. We'll now jump into the error correction, because I think this is the most important one for this discussion. Okay. So yeah, semiconductor memory system is subject to errors, and this can be categorized as hard failure or soft errors. What's the difference? So for hard failure, there is a permanent physical defect, so that the memory cells or cells are affected. Okay, and cannot reliably store data, but become stuck at 0 or 1, or switch erratically between 0 and 1. And this can be caused by harsh environmental abuse, manufacturing defect, and wear. The solve error is actually random and is a non-destructive event that alters the content of one or more memory cells without damaging the memory. And yeah, the soft errors can be caused by power supply problems or alpha particles. Okay, so these particles result from radioactive decay and are distressingly common because radioactive nuclei are found in small quantities in nearly all materials. Yeah, both are undesirable, and most modern memory systems include logic for both detecting and also correcting this kind of errors. Okay, so see, by following this procedure or the figure shown below, the component mechanism yields one of these three results. First, that no errors are detected, that the fetch database are sent on. Second, that an error is detected and it's possible to correct the error. That is that a bits plus error correction bits are put into a character which produces corrected set of bits to be sent on. And the third condition is when an error is detected but it's not possible to correct it, meaning the condition is reported. Codes that are friend efficient are referred to as error correcting codes. And a code is characterized by the number of bit errors in a word that it can correct and detect. And there are actually many methods to do this, but one of the most used and the simplest one to correct the error is by using the Hamming code, which is devised by Sir Richard Hamming at Bell Laboratories. Okay, so we have what called the compartment for parity bits, and each parity bit is chosen so that the total amount of ones in a circle is even. Actually, there are two types of this actually. There's one type, the parity is for the even, and another type is parity is odd one. Okay, but this book choose the even one. We just stick to the convention. Okay, so a bit by bit comparison is done by taking the exclusive OR of the two inputs, and the result is called the syndrome word. And thus each bit of the syndrome is 0 or 1 according to if there is or is not much in that bit position for the two inputs. And for convenience, we would like to generate a 4-bit syndrome for 8-bit data with the following characteristic. Okay, this is an example for only 8-bit data word. So if this syndrome contains all zeros, then no error has been detected. If the syndrome contains one and only one bit set to 1, then an error has occurred in one of the 4 check bits, that no correction is needed. But if the syndrome contains more than one bit set to 1, the denominator value of the syndrome indicates the position of the data bit in error, and this data bit is inverted for the correction mechanism. Okay, so the book has shown you very clearly how to do the correction using the Hamming code. I'll not explain it. This is all about the XOR operation. That's also why I've explained to you how to do the logical operation on XOR, OR, and NAND XOR, because this is how you do this in this chapter. Also, so the code that just described is known as single error correcting code, or SEC code. And more commonly, the semiconductor memory is equipped with a single error correcting, double error detecting code. Okay, is shown in the figure above. Okay, so this mechanism, an error connecting code, it enhances the reliability of the memory at the cost of added complexity. Okay, so with a 1-bit per chip organization that code is generally considered adequate. Then we're going to see how to do advanced DRAM organization. Okay, so we know that the basic building block of memory remains the DRAM chip, and as it has for decades until recently, there has been no significant change in DRAM architecture. Okay, you can see that the performance coverage of some DRAM alternatives, but we have seen that one attack on the performance profile of the DRAM main memory has to be insert one or more level of high-speed SRAM case between the DRAM main memory and the processor. But SRAM is much faster than DRAM, and expanding case size beyond a certain point yields diminishing returns. So actually, there's a number of enhancements to do with the basic DRAMs in recent years. The scheme is that we are using SDRAM, DDR DRAM, and RDRAM. Okay, let's discuss this for today's lesson. The first one is SRAM, or synchronous DRAM. SDRAM, I mean. Okay. So actually, unlike the traditional DRAM, which is asynchronous, that is SDRAM, it sends data with the processor synchronized to an external clock signal and running at full speed of the processor memory bus without imposing wait state. So in a typical DRAM, that the processor presents addresses and control efforts to the memory, indicating that set of data A particular location in memory should be either read from or written to the DRAM. And after a delay, the access time, the DRAM either writes or writes the data. And during the access time delay, then the DRAM performs various internal functions such as activating the high capacitance hold of the row and the column line, sensing the data, routing the data out through the output buffer. And the processor must simply wait through the delay, slowing system performance. With synchronous access, then the DRAM moves data in and out under control of the system clock. Okay, so this is the main thing to be understood here. So SDRAM employs a burst mode to eliminate the address setup time and row and column line pre-adjust time after the first access. This mode is useful when all bits to be accessed are in sequence and in the same row of the array as the initial access. Okay. And there's now an enhanced version of the SDRAM which is known as double data rate SDRAM, DDR SDRAM, that overcomes the only per cycle limitation. Okay, which this DDR SDRAM can send data to the processor twice per clock cycle. Now we discuss Rambus DRAM or RDRAM. Okay, which is developed by Rambus. Okay, so RDRAM are vertically packaged with all pins on one side, and special RDRAM bus delivers address and control information using an asynchronous block-oriented protocol. So you see, the configuration of RDRAM consists of control and number of RDRAM modules that connect it via a common bus. And the control is at one end of the configuration, and the far end of the bus is parallel termination of the bus line. There is also a clock signal that starts at the far end of the controller that propagates through the controller end and then loops back. And an RDRAM module then sends data to the controller synchronously to the clock to the master, and the controller sends data to the RDRAM synchronously with the clock signal in the opposite direction. Then we have DDR SDRAM. So SDRAM is limited by the fact that it can only send data to the processor once per bus clock cycle. So there are new versions that are introduced, which is called double data rate SDRAM, which can send data twice per clock cycle. Okay, once on the rising edge and once on the falling edge. Okay, you can see from the timing diagram that is done 2 times, right? So there have been 2 generations of improvement to the DDR technology. So DDR2 increases data transfer by increasing the operational frequency of the RAM chip, and is increasing the prefix buffer from 2 bits to the 4 bits per chip. And the prefix buffer is a memory case located on the RAM chip. So this buffer enables the RAM chip to preposition bits to be placed on the database as rapidly as possible. And the second improvement, the second generation of the DDR is called DDR3, which introduced in 2007. Increase the prefix buffer size to 8 bits. Next, we have case DRAM. I think this is the last lesson for today, right? Okay. So for case DRAM, okay, it integrates a small SRAM case into a generic DRAM. Okay, so it can be used in 2 ways. First, it can be used as true case, consisting of a number of 64-bit lines. So the case mode of the CD-ROM is effective for ordinary random access to memory. And the SDRAM and the SRAM on the CD-ROM can also be used as buffer actually to support the serial access of block of data. Okay, so we are done with the internal memory, the main memory. I always say main memory. Next lesson, we will start to discuss external memory, and we will soon come to the end of the computer science concept exploration, and we will start doing some programming. First, maybe I'll shortly introduce you with assembly, and later we'll go to C++, Java, and Python, and some web programming. Okay, So yeah, I think that's for today. It's enough. Yeah. So yeah, here's some quote that I want to share to you for today. Jimmy Dean once said that I can't change the direction of the wind, but I can adjust my sails to always reach my destinations. So that's good for you. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https ://science with xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.